Okay, so second problem that I'm picking, it's a variation of first one. Here, what we are doing is, let's say you are given array A. Let me pick same two examples. Okay, what is the change you are observing in this example? Previous versus this example, what is the change? Yeah, A has extra space. Awesome. Good observation, Lakshmi Jana. So this time the question is, tweak is, given array A of size an plus bn. So an is number of elements that are filled. Remaining are unfilled spaces. So A is a bigger array. Yes. Given array A of size an plus bn. And another array B, both sorted. Fill array A in such a way that it contains all elements in sorted order. Okay, and our goal is to modify array A in sorted order. Now, I want you to think on this problem again, and whatever solution comes to your mind, I want you to again type in the chat time and space complexity of your approach. I'm not asking code, keep that in mind. I'm asking you to think on this problem, and whatever approach you have, I want you to type time and space complexity of your approach. You can take help of our previous solutions we discussed. Some of the previous solutions may be applicable to solve this problem. Okay, so Deepya has a solution an into bn. Yeah, what about others? Tushara has an into bn. Okay, Shriya has an into bn. Yeah, guys, I want responses from everyone. I hope everyone will have at least one solution ready. So our first approach, take another array C, copy an into that, copy B into that, merge the results, and then copy C back to A. Will this solution be applicable to our next problem? Can we apply this solution to the next problem? Yes or no? Just exact same solution. We don't care A has extra space. In place of printing, I'll replace copy B to A, C to A. This solution will work. Okay, first solution has applicability, but we know this solution was n square or n log n solution. Coming to second one, take another array C, copy A into C, and then insert B into A. Now, if you look at this solution, can we apply this solution and say like first two steps are already taken care? A already has elements of it. Now, B elements you are inserting one by one. So rather than taking array C, we are doing insertion of elements of B in array A. Second solution is applicable. And I believe that is what people are saying. It is an into bn solution they have. So if we use approach 2, then what essentially we are doing is A already has its elements. Let's start with minus 11. Look from back side. Whatever elements are bigger than minus 11, keep shifting them to right. Create space for inserting minus 11. And we can use insertion sort approach. And to insert every element of B in already sorted array A, worst case, we'll have to shift A n elements and time complexity of that will be an into bn. So our approach to where we have an into bn solution, space complexity wise, here we are better because A already has space. This is our approach to applicable here. Coming to analyze approach 3. In approach 3, we use two-pointer technique. Can we somehow apply two-pointer technique to solve this problem? That's what I want everyone to think. Are you able to see any approach using two-pointer technique? Just a small hint I want to give you. Two-pointer doesn't always mean you are starting from the beginning. Earlier, we started from beginning of A array and B array and we were comparing them. Two-pointer does not essentially have to start from the beginning. Or if I say to you, apply two-pointer technique from the beginning, can we do like this? Take C of size an plus bn. Now you have taken one new array. Can you apply two-pointer technique, compare and copy that into C? Two-pointer and store results in C and then copy C back to A. Will this work? So you took another array C, same size as A, compare -20, -11. So basically you are running the loop until unless these elements and these elements get merged. If we use this approach, what will be the time complexity of approach 3? An plus bn. What will be the space complexity of third approach? An plus bn. Okay. Now the question I'm asking you is, can you tweak approach 3 and make it approach 4, but think of applying two-pointer technique not at the beginning? Yeah, so Nidhi is saying, if we compare from back, okay, let's analyze what she's trying to say. She's saying, let's compare 90 and 120. If you compare 90 and 120, what conclusion can you draw? Which element can you take out of these two? You will take 120, which is maximum element, and where will you copy that element? Yes, you will put that at the last index of array A, because that's the free space. So can we say here we are saying take AI is equal to an minus 1. An is 5, that means the filled elements. Bi is equal to bn minus 1 and ci is equal to an plus bn minus 1. So ci pointer is starting from here. Now if you come from the back side, compare 90 and 120. 120 is bigger, you copy here. After that, shift bi back. Now you will compare 90 and 100. You will copy 100 to the second last place. Then you will compare 90 and 11. 90 is bigger, you will copy 90 to the third last place, and so on. So we are able to apply two-pointer technique from back side of two arrays. If you use that approach, if you come from backside, what will be the time and space complexity of this solution? Yes, what is the time and space complexity of this solution? Yeah, time is same as an plus bn, and our space complexity has improved to big of 1. We don't need another array C. So that becomes our approach for TC of an plus bn and space complexity of big of 1 constant. Now take some time and quickly write code for this. Again, you will be writing it like a function. So return type is void because A already has space. Then you are saying merge sorted arrays. So you have list of int of A. A has ample space. An is the elements. An is not the size of array. An is number of elements that have been filled in A. Then list of int of B. Size of A and B you can figure out easily. But reason I have given you An separately is here you can understand An is not equal to A dot size. Just remember that. N is number of filled elements in A. Here we have 5 elements filled. That is An. But rest of the places are the size of B array. Okay. So I want this function to be completed by all of you. A, An, and B. So in Python, that will be the signature. So go ahead and quickly convert this approach, this idea into code. And in the meanwhile, if anybody has any doubts on whatever we have discussed so far, technique, complexity analysis, feel free to utilize this opportunity to ask your doubts. And if there are no doubts, I am assuming everyone is able to grasp, is able to follow what we are discussing. And it should not take much time for converting this idea to code for you. I want you to code only approach 4. First 3 approaches were thought development, and last one, since it is efficient approach, you're converting that into code. And don't type your code in computer. Right now, I want you to work with pen and paper. So make sure you're writing code on pen and paper. It will clarify a lot of things for you. In interviews, you don't get online compilers. So you have to code on pen and paper or a whiteboard or a simple Word document if it is an online interview. Okay, one response, Nidhi is done. Yeah, I'll wait for a few more people to complete it. Yeah, Lakshmi, go on.
Yeah, I have taken AI index at an minus 1 and BI at bn minus 1. And
Yeah.
bn equals to b dot size.
It is b dot size minus 1, let's say. Okay.
Oh, okay. Mm. And CA index, which is equals to n plus bn minus 1.
Or can I say a dot size minus 1?
Yeah, yes.
Okay. Then
And then while loop, AI if AI greater than or equal to 0 or BI greater than or equal to 0.
or pi is greater than equal to 0.
Yes.
Okay.
If AI less than 0,
Okay, that means
A of CI equals to B of BI.
so that means first array got over and you are left with only elements in the second array. Okay.
Yes.
Then
BI minus minus.
bi minus minus.
Then else if BI less than 0.
Okay.
A of CI equals to A of AI.
A of AI.
Then AI minus minus.
Okay.
Then again else if A of AI less than B of BJ. I mean BI. A of CI equals to B of BI.
Okay.
And again BI minus minus.
Okay.
Else A of CI equals to A of AI. BI minus minus. After else statement, CI minus minus.
Okay, yeah. So basically we have to decrement CI in all the cases, and
yes,
rather than putting this statement in every case, you have preferred to keep it outside, which is fair. Okay, anything else?
Nothing, sir. That's it.
Okay, fair. Thanks, Lakshmi Priya.
Thank you, sir.
In the while condition, and can be written. Yes, that is correct. In the while condition, we can write and the first two if conditions can be skipped. If we do that, if we write and here and if we skip these two statements, then of course remaining elements we have to take care outside the while loop, right, Nidhi? Because first while loop will complete in that case when one array get over. Now, even if they are already sorted, you will have to have a loop outside because, oh yeah, that's a very good point. Yeah, thanks for bringing it up. Okay, so Nidhi is saying that for this particular problem, if you are coming from backside, if BI did not get over, AI got over, that means we have already sorted both of them. Is everyone agreeing with Nidhi's observation? She's saying that putting and here will not require two outside loops. So if you take this, she's saying even if we remove this and we put and here, this should be sufficient. Does everyone agree to the point Nidhi is making? Let's get to our example and try to understand what makes her say this. Yeah, so let's take this example here. Now, if you are copying, if you are comparing back from backside, for now, let me take them as positive elements, 11, 15. If this be the case, which array will get over first? When you're comparing from backside, you compare these two, 120 moves here. Then you compare 90 and 100 moves here. Which array will get over? B array will get over. And if B array gets over, that means the last element, 11 of B will be placed at this place and 90 would have shifted already. Now, rest of the elements are already there in A. Do you really need to go and touch them? Let's see. If array A we are seeing from backside, this is array A. When you compare 120 and 90, you know the 120 moves here. Then you compare 100 and 90, you know 100 moves here. Then you compare 21 and 90, who moves? Compare 21 and 90, 90 moves. And when 90 moves, now your comparison point will be 6. Compare 6 and 21, who moves? Out of 6 and 21? Because your A pointer shifted back. So now you're not at 90. When you copied A element, AI minus minus happens. So you're comparing 6 and 21. Who moves? 21 moves. So 21 comes here. Then pointer this will come. Now you're comparing 15 and 6. So 15 will move here. Now you're comparing 13 and 6. So 13 will move here. Now you're comparing 11 and 6. So 11 will move here. So Nidhi's point is now B array got over. This while loop will break. Now, rest of the places, A elements were already there. You don't have to do anything outside this while loop because those elements are already present and we are done. Okay. Another example you can visualize it with is, what if array A had elements as 11, 12, 13 and B had 1, 2, 3, 4, 5, 6. What will happen now? You are comparing, you are starting with AI to be 0, 1 and 2, BI to be 5. You are comparing this and this. What will be copied out of 13 and 6 here? Yeah, guys, what will be copied? 13 will be copied. So 13 moves here and 13 will stay here also. Then you're comparing 12 and 6. So 12 will move. Then you're comparing 11 and 6. 11 will move. Now A array got over. Okay, now A array got over. And we are saying, since A array got over, we are doing nothing here. In this example, is it okay to leave the algorithm here? Did we get the final answer in array A? Okay, so although Nidhi had a point, when array A got over, we are done. But when array B, sorry, when array A got over, we have to do something. When array B got over, we don't have to do anything. So in her idea, this was fine. Outside that, not needing both the loops is not acceptable. So we need one loop. So Nidhi, we will need one loop at least. If array B elements are left, they need to be copied. Is that correct? Yes. Okay. But thanks for bringing up this point. This is good observation. So we will say if while bi is greater than or equal to 0, we will continue to copy elements from B array into this. Yeah. And we don't need the other loop of AI. And we have traced that with this example. Okay. So now this becomes complete solution. Okay. So we have this problem nailed. Everyone clear with this? Are we good to move to the next problem? Okay. Let's take a next problem. Given a binary array, what is binary array? Yeah, array has zeros and ones in it. Given a binary array, we are asked to sort the array in ascending order. If I give you array as 1, 0, 1, 1, 1, 0, 0, 0, 1. We want to sort this array. What is the simplest way? What is the simplest way? Simplest way is to use built-in sort method. If you use built-in sort function, the time complexity of built-in sort function of any library is n log n. C++ have built-in sort function. Java has, Python has. That is approach 1. Where we have to write less code, we use built-in functionality. Approach 2. Let's say I prohibit you from using built-in function. What is it that we can do?
Counting zeros and ones.
Counting zeros and ones. Nidhi, you are suggesting map-based approach. There are only two values. Map will be an overkill. We can use just two variables. How many zeros are there? How many ones are there? Okay, so if we use count approach, do we need to count zeros and ones both, or one count is sufficient for us?
One count is sufficient.
One count is sufficient. So if you count zeros by writing one loop, what count of zeros are you getting? Total size is 9, zeros are 4. Total size minus 0 count will give you count of ones. So what you have to do is you have to count zeros in the array. Once you know the count, go and overwrite the array A. 4 zeros are there. First 4 elements can be overwritten and filled with zeros. Rest elements can be overwritten and filled with ones. Is that right? Okay, so you are taking count zeros is equal to 0. Now, for each element, if element is 0, you are saying count zeros to be plus plus. So you got the count back here. Now what you essentially are going to do is you are going from I is equal to 0 to n minus 1. You are simply going to say a of I is equal to 0 if I is less than count zeros, else. Is that correct? Is this logic or idea correct, or I have to make some changes? I'm saying as long as I is less than count zeros, I have to fill 0. I need your approval. This will work or not work? Okay, it is I0 less than count zeros, or I less than or equal to count zeros? Okay, let's compare these two. What should it be? It should be less than or equal, or it should be only less than? So Nidhi, double check your answer. Nidhi, you are saying it should be less than or equal. If count zeros is 4, which all indices you want to be filled with 0? 0, 1, 2, 3 or 0, 1, 2, 3, 4? Yeah, so less than is fine. Okay, so this is our approach. Ideally, this is an approach of count sort. So if you see this approach, I ask you, what is the time and space complexity for this approach? Whatever you are seeing as the steps here, whatever we have discussed, what is the time and space? Yeah, so first for loop is going to loop over entire array n. Second for loop is again looping over it. So it is n plus n, call it an plus an, which is 2an. If you have to express that as big O notation, 2an will be considered as an because we drop the constant factors. What is the space complexity of this approach? Space is constant. We just used 1 or 2 extra variables. One is for counting, another is I variable. So yeah, space is constant. Now think about it. Can we use two-pointer technique to solve this problem? Can two-pointer technique help us sort this array? Okay, people are saying yes, two-pointer technique will work. So how we apply two-pointer technique? What exactly are we doing? This is one array. So do we start from same end or we start from different ends? We start from different ends. Yes. So your I variable is at 0, j variable is at end. Now you compare. The element here is 1. Do you need 1 here, or it should have been a 0? Okay, it should be a 0. So when you see the first element is 1, you will take a pause here. You will stop here. You will say, hey, this needs a replacement. Now, right side, you see a 1 here. If you see a 1 on the right side, what will you do? You will move back, decrement. You will continue coming back as long as you find a 1, because 1 is valid. Now your initial pointer is initial variable, it has index 0. Second variable is at index an minus 2. You have 1 here, you have 0 here. What will you do? You will swap them. Okay, so swapping will make it, this will become 1 and this will become 0. And this is where your initially I pointer was. This is where your j pointer is now after the swap. Now again, we will do the same thing. I is here. It is 0, so move forward. It is 0, move forward. So I will come and stop at this point. Now coming from backside, j is at 1, move back. Here it is 0, so you stop here. I is at 1, you stop here. Now what do we do? A of I is 1, A of j is 0. Again, do a swap. So basically, you are moving 2 pointers one step at a time. Conditions are your I is 0, j is an minus 1. When do you move I? Yes, when do we move I? If it's like keep moving I forward. If A of I is 0. That is what we will do as first step. Okay. Same way, you will say keep moving j backward if A of j is 1. Okay. That means after these two steps, you have moved I, you have moved j. After these steps, what will you do? Swap. But before swap, you will check if I is still less than j, swap ai and aj. Otherwise, we are done. Is that correct?
వద్దు ఆర్డర్ అసలు వద్దు.
Manoj, can you be on mute? Yes, are we clear with this? So we will do it in a loop. This will also be a loop. This will also be a loop. And our loop will keep running as long as I is less than j. So what essentially happens in every iteration, I is moving, j is moving, and you will be declaring done when I and j cross each other. That's the whole idea of two-pointer technique. If we go with this approach, considering I and j's movement, how many positions I and j will be touching? Or basically, if I ask you, what is the time complexity of this solution? Every time I moves, it's one iteration. Every time j moves, it's one iteration. And you are done when they cross each other. So what is the time complexity of this approach? So it is n by 2 or it is n?
If we have all zeros,
If we have all zeros, very good point. If we have all zeros, it will be I will keep moving,
yes, sir. It is
j will
fine.
not move at all. And here I is less than j will be violated. So you'll not swap and your loop will break. So it will be n. If we have all zeros, it will be n, fair. If you have all ones, it will be n. If you have a mix of zeros and ones, then also can I say when I moves, at least I covers one index. When j moves, it covers index. So every index in the array you are touching at least once. You're not moving I and j together. This loop moves I, this loop moves j. Both are not moving together. So it is still n. It's not n by 2. Space complexity. Okay, what is the space complexity? Big of 1, constant. Time complexity is n, space is 1. Okay, so that solves the problem. Now, this solution is better or approach 2 is better? If I have to compare approach 2 and approach 3, which solution will you say is better? Approach 3 is better because it reduces time complexity by half. Here, bigger wise, they are same. But absolute terms, practical terms, if you see, second one is a little more efficient than the first one. Nidhi, omega notation is not used a lot, theta and omega. Like those are more important from academic angle, not from the problem solving angle. So, I mean, they are not typically used during the interviews. Yeah, we care about optimizing our worst case. Okay, so we are good with sorting the binary array. Now, one more question on similar lines. That will be our last question for today. We will continue two-pointer technique because two-pointer technique encompasses various segments. Today, I'm discussing just simple one array or two array problems starting from same ends or different ends. We will gradually take it to sliding window technique, pair problems, triplets problems. So there is a good ground to cover on two-pointer techniques. So we will continue these sessions. I'll not have it tomorrow. I'll update you when we will have next session, but I'll give you exercises before the next session that you can work on. You can apply whatever you're learning today. Okay, so next problem is you are given the array, sort ternary array. So earlier we were sorting binary array. Binary array had 0 and 1s. So ternary array should have, ternary arrays will have 0, 1 and 2. Okay, so you are having a array which has zeros, ones and twos. And you have to sort this array. So previous two solutions we discussed. This was our count sort solution. Approach 1 will still be applicable. We can use a built-in sort, but that will be an overkill. Count sort will still be applicable, but now for count sort, how many variables you will have to use? 2 variables are sufficient. If you use 3, you will be counting how many zeros, how many ones are there, and how many twos are there. But if you know count of ones and zeros, you can reduce the count of twos. So 2 variables are sufficient. Okay, so these two approaches are pretty evident, pretty clear that they will solve the problem, but we want to see the applicability of third approach for solving this problem. Can we solve this problem with two-pointer technique and a slight twist? Okay, so Aparna says take 3 pointers. Pratisha says take 3 pointers. Yes, there is a standard algorithm. Its name is Dutch national flag problem. So that says like you have 3 kind of flags and you have to sort them. This problem also gets asked, array has A, B, and C in some jumbled order. These are the characters. You have to sort the array. Sometimes it is red, green balls that you have to sort. So Dutch national flag is a standard name of this algorithm, which uses two-pointer technique to solve the problem. So what essentially we do, we start 1 pointer here, we start 1 pointer here. Now, when you see a 2, where should 2 go? When you see a 2 here, 2 should go back. When you see a 0 here, where should 0 go? Front. So basically, if first element is 2 and last element is 0, the simple solution is to swap. Right? Yeah. The challenge will come, like here we can do the swap. Challenge will come when you see a 1. What you should do when you see a 1? When you see a 1, you should actually continue. So ultimately, you will have a variable. AI will be at a point where next 0 should be inserted. You will have AI as 1 pointer out of 3 pointer technique, where next 0 should be inserted. BI, you will take where next 2 should be inserted. And CI is, we will keep it always moving. Okay, this is the strategy, this is the idea we will take. Okay, so initially your AI will be 0. This is the place where we are assuming next 0 should come. Yeah, 1 will automatically get sorted. That's a fair point, Nitya. Your CI will also start with 0. Your BI will be at the last index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So BI is at 10. Okay, this is our starting point. These are the 3 pointers we have. We'll keep in mind AI will always hold the ground at a place where next zero should come. Now, if you examine A of AI, A of AI is 2. Should we move AI pointer? It should not move. AI should not move because AI will always keep pointing to a place where zero should come. Zero should come here. So AI will hold the ground here. Okay. Now let's look at CI. CI will always move. So CI will go and look at the next element, 0. So CI is moving. When you are at 0, when CI is at 0, where should this 0 be placed? When you see a 0, what should we do with the 0? Yeah, 0 should be swapped with A of AI because AI is telling us where the 0 should be inserted. So whenever you see a 0, swap it with A of AI. And once you swap them, it becomes 0, it becomes 2. Now, do you think AI should change? Whenever you swap with AI, should AI change? AI should be incremented because now this place got 0. So AI should come to a point that, hey, this is where the next 0 should come. So AI moves only when you find a 0 and you're swapping with A of AI. Okay, same way if you're coming back, look at this. This is a 0. Oh, sorry. This is where BI will hold the ground. BI will keep sitting here. Here 2 should come. BI will not move. So CI will come to 1. When CI comes to 1, wait, we did a swap. We did a swap here. So CI is still at this index. Now CI is at a value. The value at A of CI is 2. Where should 2 go? Where should 2 go? It should be swapped with the end. So put 2 here, put 0 here. And BI should decrement. BI should reach this point. That, hey, now the next 2 should be coming here. And now CI comes to 1. If CI comes to 1, what should we do? If CI comes to 1, what should we do? We should move forward. We should not touch anything. We should not do anything. AI is sitting at this position, BI is sitting at this, and CI will continue to move. Now CI comes to 2. What should we do? When CI comes to 2, what should we do? We should swap with BI. So whenever you see a 2, swap with A of BI. Whenever you see a 0, swap with A of AI. And whenever you see a 1, continue moving forward. That's the whole idea. And this is the guidance we are using. AI will always keep guiding us where 0 should come. BI will keep guiding us where 2 should come. Sorry. Yeah, and this is a kind of must know algo, Dutch national flag. Are we good with whatever problems we discussed today? Were they helpful? Hey guys, are we feeling good about 2-pointer technique? Did we learn something new? Okay. So when we are doing 2-pointer technique, I'm going to point you to certain exercises that you have to do before our next class. We will continue this topic. There are many interesting optimization problems on 2-pointer technique that we will be covering. In upcoming sessions, we will be covering pairs problems, sub-array problems, triplets problems. You will have they are all applications of 2-pointer technique. So we will have good coverage of the problems. With whatever I have covered today, with this, you will be able to solve some problems. So I'm going to point you to certain problems and the plan what we have to do. Let me just discuss that and then we will close the session.